Hi, my name is Sergey Levine, and today I'm going to talk about how we can use large-scale data-driven robotic learning to build more general-purpose robotic learning systems. So, how do we get generalist robots? If we want to start answering this question, let's instead ask a more basic question: how do we get generalist models in other fields of machine learning? If we really want to build models that can solve a broad range of tasks rather than just a single task, typically, the thing that we have to think about first is how to get sufficiently general purpose data. And here we get a kind of continuum where we can start with simple methods that can use small amounts of well-curated data, like traditional shallow machine learning methods, move on to larger models that can use broader sources of labeled data, and then, of course, the kind of thing that has been very much the way to approach these problems in the last couple of years, which is to use a large-scale unsupervised machine learning with even broader data sources. And what we see is a big increase in the generality of the models each step that we take. So we can think of these things as being on a continuum where the further we move to the right, the larger our data sets become, which means that our models are more general purpose. For example, large language models that could then be adapted either via prompting or fine-tuning to a broad range of different downstream tasks. But at the same time, we also have weaker labels because it's increasingly harder and harder to get data sets that are large enough for these generalist models that are also strongly labeled. And we also need to make fewer assumptions. For example, we might not be able to assume that our data consists of paired XY tuples. Maybe it's just unstructured text or unstructured images. Perhaps we need to deal with the fact that more and more of our data might be irrelevant to the task, and we have to use larger, higher capacity models that can pull out the signal even from extremely diverse data sources. So to get generalist models, the biggest enabling factor is the ability to use more data. But that's about more than just collecting lots of data. It's also about building algorithms that can effectively utilize it. So how do we design robotic learning methods that can also use more and more data? And we can think of a similar kind of continuum for robotics, where maybe on the left side we have single task, single robot methods that acquire a single behavior, either from a hand-designed reward function or from a task-specific set of demonstrations. From there, we could imagine going to multitask settings, perhaps a multitask setting with demonstration data, or even a multitask setting with suboptimal data that could be collected autonomously. From there, we could go to a multi-robot setting, and all the way to a setting where we might also include data that doesn't even come from robots, like video data. So again, the further we go to the right, the bigger our data sets become, the more general our models could be because they're trained on broader and more diverse data sources, but also the weaker the labels and the fewer assumptions we're allowed to make. Where on the far right, we might not even be able to assume that the data comes from a robotic system. With suboptimal data, we might not be able to assume that it consists of trajectories that are optimal for any well-defined task. The key point I want to make with today's talk is that we can develop general methods that can use all of these sources of data. And while I will present a variety of different techniques, hopefully I'll get across the idea that all of these methods are really driving towards some unified whole, and that perhaps in the future we will see a yet to be developed single robotic learning method that can utilize all these data sources, much like how self-supervised or unsupervised training for language models, computer vision, and other domains can utilize all available data sources. So I'm going to talk about different ways of using diverse robot data that will kind of build up towards greater and greater generality. I'll start with goal condition policies. Then I'll discuss how offline RL with rapid fine-tuning can enable utilizing suboptimal data and also getting better results. I'll talk about learning from videos and action-free data. And I'll discuss at the end some very recent work on learning from a huge variety of different robots. So let's start with the goal condition policies. We've been studying this topic quite a lot in my lab. Most recently, we've been investigating collecting data sets that are particularly effective for enabling generalist robotic policies. The latest data set that we released is called Bridge Data v2. This is work led by Homer Walker and in collaboration with many others. The second iteration of the Bridge data set consists of over 60,000 trajectories that are all demonstration trajectories collected by a teleoperation, hundreds of objects, full language annotations for all the trajectories for those that want to study language conditioning, 24 different environments, and we've been able to confirm that policies trained on Bridge v2 can successfully run at other institutions. So because there's so much variety of environments, you can actually get generalizable policies that can not only perform many tasks, but can do so in many settings, which makes it suitable for other researchers to use. But what I want to talk about today is how we can use Bridge Data v2 to train goal conditioning policies that can perform a huge range of different tasks, and then how we can take these goal conditioning policies and adapt them to a wide range of different downstream uses. So the idea is going to be very simple. We're going to train neural network policies that take in the current image that the robot sees, and then a photograph of the goal that we want the robot to accomplish. So if we want the robot to sweep this dirt, then the goal image has the dirt correctly swept over to the side, and then the policy outputs the action that the robot is supposed to perform. Now, at this point, some of you might be objecting that, well, in reality, we might not want to specify all of our tasks with goal images, and that's perfectly fine. We're actually going to see how we can train these goal condition policies, and that's very good because they can use lots of data, but then we can actually adapt them to other ways of specifying tasks also. So they sort of serve as a self-supervised substrate on which we can build other things, a kind of foundation, much like how language models serve as foundations for all sorts of NLP tasks. But first, let's talk about how we train these things. So the training procedure, the most basic one, is actually extremely simple. We can make it much more powerful by incorporating reinforcement learning, but a simple supervised learning procedure proceeds as follows. We take the data set, and we sample a trajectory from that data set, and then we pick 2 time steps. We know that the action shown in red at the time step in green is an action that can lead to the subsequent orange state, which means that we can construct a training tuple consisting of the first time step green, the second one orange, and the action that was taken in red, and simply use this as a label data set. So we can sample many of these green, orange, red tuples from all the trajectories in the data set, create a supervised training set, and use that to train our goal condition policy. And this is basically the essence of goal condition BC. Now, again, we can use much more sophisticated ways of training these policies, but even this basic recipe is already extremely powerful. It's powerful because we can use extremely diverse sources of data. Any robotic trajectory is suitable for this, and even if the trajectory consists of demonstrations for a particular task, in a sense, we're actually learning a lot more from that trajectory than just that task alone, because we're learning to associate whatever outcome was seen with the action that was taken. And you could imagine any trajectory is actually a good example for a variety of different behaviors. If you place an object in a particular location, it's a good example for picking and placing that object. It's a good example of placing it in a particular location. It's a good example of placing it in a particular pose. So all these things are captured by goal condition BC. And if we have the right data set, these kinds of policies can be immensely powerful. So there's been a lot of work on goal condition BC that oftentimes uses a relatively small data set and tries to improve the methods. But what we found with Bridge v2 was that just by improving the data set, we could get extremely powerful goal condition policies. So this is showing essentially this approach on the left being trained on Bridge v2, and the single policy can actually perform all of these tasks. So this is the same policy doing all of these, sweeping dirt, folding cloth, manipulating furniture, all these things. And then we can actually take these policies and we can use them for some downstream applications. For example, one of the ways that we could improve instruction following with goal conditioning is if we have a setting where we have lots of unlabeled data, so this might be more readily available data, where we just have trajectories and actions, and then some subset of data that is labeled with language instructions like put the pan on the towel, right? And perhaps what we'd like to do is use a little bit of the supervised data with a large amount of unlabeled data to get more effective instruction following policies. One great way to do that is we can actually learn goal representations that align changes in state, so S0 through G, with language. This is a little bit like CLIP, except that whereas CLIP aligns images and language, this aligns pairs of initial state and goal with language, because language actually describes a change. So we really need to align a tuple with the language, a transition. And then we can just train the policy on top of this representation with an additional alignment loss that encourages the representation of goals to remain aligned between the language representation and the state goal representation. And this can actually get us a very powerful language condition policy that can follow a wide range of different instructions. And in our evaluation, we've actually shown that this policy, which we call GRIF, shown in orange, significantly outperforms the success rate of alternative approaches. The ones that we compare to are BCZ, which is basically a classic language conditioned behavior cloning method, and learning language from play, which is a method that also uses both labeled and unlabeled data, but without this type of alignment strategy. But the takeaway from this is that if we can learn very good goal condition policies, we can actually improve our ability to follow instructions by using these alignment losses with only a moderate amount of data that is actually labeled with language. So this provides us with a really good way to use weakly labeled data. The other thing we can do is we can use the goal condition policies directly to carry out language instructions if we combine them with image generation methods. And that's actually a really nice way to combine even more sources of data. So the language conditioned image generation can utilize data from other sources, like data sets from the web, and the goal condition policies can utilize even unlabeled robot data. So we explored this approach recently in a paper that we call SUSY, Subgoal Synthesis by Image Editing, where the idea is that we'll take Stable Diffusion 1.4 and we'll fine-tune it so that it generates future robot videos given a starting state and an instruction like put the orange crayon in the wooden bowl. This model benefits from pre-training on internet scale data and is then fine-tuned on robot trajectories that are annotated with language. So the model basically predicts a sub-goal, like for example, if you tell it, put the orange crayon in the wooden bowl, it might predict a frame where the robot is grasping the crayon. And then we use this goal condition BC policy, trained exactly in the way that I described previously with Bridge V2, to actually carry out that sub-goal. And this is a really nice combination because the sub-goal makes it easier for the goal condition BC policy to carry out the task, and the internet data makes it easier for the image generation model to produce good sub-goals. If we combine pre-training on video, in this case it's something, with fine-tuning on some amount of robot data, we can produce very nice sub-goals for a wide range of different tasks, like fold the cloth from the bottom right to the top left corner, open the cabinet, put the mushroom on the blue towel, etc. Now notice the sub-goals are not actually showing what happens when the task is fully complete, they're just showing the next logical step, and that's actually better for downstream goal condition BC. And then we can put these together and we can actually get effective policies. So you can see in the top right, we show the generated sub-goals from the model, and then we see the robot execution actually carrying out that sub-goal. And it can open the microwave with this complex motion that involves putting the roper behind the microwave door and then prying it open. And in the lower right, you can see some side-by-side comparisons that show the SUSY method for the open the drawer task and the open the microwave task. And next to it, we see a baseline, which is regular goal condition BC, where the goal is actually the final frame of the task that is actually a ground truth frame. It's actually provided by a person. So this is a kind of oracle showing that even if you give goal condition BC the correct final frame, the SUSY method is actually better because that image generation model produces good sub-goals. And I think this is a really nice example of how more readily available data, in this case, image generation data from the web, can be combined with more readily available robot data, in this case, unlabeled trajectories, to get a system that can carry out language instructions. Okay, now so far, we've entirely relied on supervised learning, but next let's talk about how reinforcement learning can come into the picture and let us use things like suboptimal data or enable much more rapid fine-tuning. So first, what do we expect RL to actually be able to do when we combine it with data? Well, if we're using data, that means that a big chunk of what we're going to be utilizing is offline RL. Offline RL methods are RL methods that run on static data sets. We're actually going to bring in online RL later, but we'll start with offline RL. So the simple intuition behind offline RL is maybe it's a little bit like imitation learning. Maybe you get data that kind of performs your task, and then you learn how to perform it similarly to the data. That's okay, but I think that's a far cry from the full capability of what RL can do. A better intuition is that offline RL is about kind of getting order from chaos. So if you imagine that you have many suboptimal trajectories that all do a wide variety of different things, but what you really want is to get from the green circle to the orange circle, offline RL can figure out how to recombine parts of the trajectories that you've seen to carry out the tasks that you really want more optimally. In the most obvious sense, if you've seen examples of going from A to B and B to C, you ought to be able to figure out that you can go from A to C. But in reality, this kind of happens everywhere at once. So if you have a bunch of behaviors that are all suboptimal in different ways, if you take the most optimal part of each behavior in each place, you might get an overall trajectory that is significantly more optimal than any of the data by itself. And that's immensely powerful. So most current offline RL methods are based on Q function estimation. I won't go into too much detail about the technical aspects of this. If you want to learn more about it, I encourage you to check out these two papers, Conservative Q learning and Implicit Q learning. These are the foundation for most of the most effective offline RL methods today. There are many more works on this, of course. These are just the papers I would recommend to you to start with. What I'm going to talk about is how those methods can be leveraged for robotic learning, and at that level of abstraction, you can basically think of all of these methods as exposing a simple interface. Take a data set of transitions, state actions, and next states, learn value functions from those transitions, and then use them to perform tasks more effectively. So first, let's see how we could take a large data set of demonstrations, combine it with negative data that failed at the task, and see how offline RL can allow us to do better. And this is going to be based on some experiments that were done at Google, led by Yevgen Chebatar and Quan Vong, in this paper that we call Q-transformer. So the history of this work is that we initially actually were studying language conditioned imitation learning in this paper called RT1. RT1 has come to be a very well-known paper. The basic concept behind RT1 was to scale up language conditioned imitation. Take a large transformer-based policy, train it on a large data set of data with demonstrations and language annotations, and then see how well it can generalize combinatorially to different kinds of instructions. And RT1 enables some pretty cool stuff. For example, we could use a high-level language model planner to specify sub-goals in language, in this case, not as images. And then RT1 can carry out those sub-goals, carry on instructions like open the drawer, pick up the chips, and so on, to perform some compound tasks like bring me the rice chips from the drawer. So RT1 is a very effective system. The problem with RT1 is that it's a little bit too far to the left on that spectrum, where it requires fairly strongly labeled data. It has to be demonstration data, and it has to be described with language instructions. But what if we take RT1 and we run it for many, many trials on a real robot, and those trials, some of which are unsuccessful, right? In the actual experiment, what we actually did, just to keep the comparison fair, is we ran RT1. We actually collected a larger data set. It was much bigger than 20,000, of which maybe some percentage was successful. We actually threw out the successful trials and kept just the unsuccessful trials, so we could have a head-to-head comparison of imitation learning with the 38,000 initial demonstrations versus offline RL, where we also add the 20,000 unsuccessful trials. Of course, if we also added the successful trials, this would be even better, but we want to have a controlled experiment. And then we're going to take this combination and we're going to give it to offline RL. Notice that the data set is not getting that much bigger. We could have collected many more unsuccessful trials because they're very cheap compared to demonstrations, but even with 20,000, we were able to see some pretty impressive improvements. And then we took this and we used it to train an offline RL trained RT1 model that could incorporate these unsuccessful trials. You can't incorporate them with imitation learning, of course, but if you use offline RL, then you can make use of them. The particular recipe in Q-transformer is a little bit more elaborate than the standard offline RL method because the RT1 model uses discretized, tokenized actions. So what we actually did in Q-transformer is we treated every dimension of the discretized action as a separate time step in a higher level MDP. And now Q-learning is actually not just done across time steps, but it's also done across dimensions of a single time step. Now, that has both pros and cons. One of the advantages of this is that now we have a discrete action Q-learning problem. One of the disadvantages is that the horizon goes up by the number of dimensions. But notice that this doesn't suffer from the curse of dimensionality because we're actually treating each action dimension as a separate decision. So dynamic programming already accounts for the combinatorial combination of possible per dimension values. So that's actually a very effective way to handle discretization if you have high dimensional actions. And of course, you can use powerful transformer models naturally because the action representation is tokenized. And then the actual algorithm is very similar to conservative Q-learning. And what we saw is that you could use this to train with offline RL to get a policy that could follow diverse language instructions, and it actually followed it significantly better than just a supervised version of RT1. So this is evaluating on a variety of challenging tasks. There are kind of three categories of tasks, but within each category, there's a large number of different language instructions. And this is the column for the classic supervised trained RT1. The other methods are IQL and decision transformers. So these are alternative offline RL methods. And then the Q-transformer is the one that uses this tokenized actions. And you can see that that more than doubles the performance of the original imitation learning method by including those negative examples. So offline RL really does broaden the range of data sets that you could use. But you could also use offline RL as a way to help you learn a new task. So what if we don't just want to do better on the task we've got? What if we want to actually use it to help us fine-tune to a new task? So what we could do is we could take, these are experiments that were done using the bridge data set. We can take data from a variety of tasks. We can train our multitask policy with offline RL. In this case, we're just going to do it by conditioning on a one-hot indicator, but we could do it with language as well. This was using an earlier version of the bridge data set, which was a little bit smaller. It was only 12,000 demos at the time. And that gives us a pre-trained offline RL multitask policy. This was done in this case with CQL. And then when we get a new task, let's say we have 10 trials, 10 example demonstrations for a new task, we would just reserve that last entry in that one-hot vector for the fine-tuning task, condition on that last entry, and then we would fine-tune the policy, again with offline RL, using those 10 demos. In practice, we actually mix each batch to have some of the old data and some of the new data so that we don't forget. But more or less, it's just a straight-up offline RL pre-training fine-tuning method. And the goal is to see how well we can master this new task using just 10 trials. So we're going to be learning entirely new skills after pre-training on the bridge data set. Of course, the new skills are structurally similar. So in this case, I believe the difference is that it's a new environment, and then you're putting a new object into a new container. But you've seen examples of putting objects in containers in the prior data. So in the experiments, we saw that this offline RL pre-training fine-tuning method, which we call PTR, pre-training for robots, did quite a bit better than many of the alternatives. In particular, it did significantly better than pre-training with behavior cloning. It also did significantly better than fine-tuning with behavior cloning. The method also got better and better as we increased the size of the neural net backbone. So here, this plot is showing the performance on the downstream fine-tuning task, the open door task, and the pick and place task. And the x-axis is the size of the neural network backbone. And you can see that as the backbone gets bigger, the fine-tuning performance improves and actually keeps getting better, especially for the harder pick and place task. The other thing to notice is that this way of pre-training significantly outperforms prior methods that were designed as kind of computer vision representation learning techniques like R3M and MAE. You can see that PTR does much, much better than all of these approaches. So pre-training on the diverse multi-robot data with offline RL really does give you better representations for downstream fine-tuning. But how about online RL fine-tuning? Well, we can do that as well. So what we can do is we can pre-train with offline RL in the bridge data set, and then we can use that using an algorithm called CalQL, which is an online RL extension of CQL, to do online RL fine-tuning. So when we first attempt a task, in this case open the microwave, maybe it doesn't succeed from the pre-training. This is still bootstrapped with a small number of demonstrations, but this task is hard enough that it fails on the first attempt. If we run additional online RL fine-tuning, then over time it starts getting better at grasping the handle and eventually actually succeeds at opening. And in these experiments, we found that going from just the offline version to online fine-tuning improved up to 73% from 53% across the range of positions, and on the out-of-distribution positions, the ones that were not seen in those bootstrapping demonstration trials, it actually went from 13% to 60%. So it's quite effective to use offline RL as initialization for online RL. And online RL, of course, can use autonomous data, so that even further broadens the range of data sets that you could use. So offline RL pre-training can enable acquisition of new skills with 10 to 20 demos, and it allows cheap autonomous data to fine-tune those skills even further. Okay, but now let's try to broaden the set of data sets we can use even further by including videos. So how should we think about video data? Well, we've got our robot data. Robot data sets have to come from robots, so that's an additional cost. They're often bigger than you think, and I'll talk more about that later, but they're still going to be limited in their size. Video data sets can be mined from the web, they can be recorded from humans, robots can observe people attempting tasks, so that's a very rich source of data. But what does video data tell us? Because it doesn't necessarily tell us how a robot should perform the task, and it doesn't contain rewards or value or actions, so that's a big problem. Well, here's a little bit of intuition about what we can learn from video data. Let's say that you observe a trajectory in a video. What you can figure out is that orange comes after green. That's pretty natural. But imagine that you see another trajectory that goes to a state blue that is similar to green, but then afterwards reaches a very different state yellow. Well, in this case, you can figure out that green and blue are kind of similar, so you ought to be able to infer that green can lead to either orange or yellow. And in particular, if you assume that any variability in the video is controllable, meaning that there's not a lot of stochasticity, which is not really a true assumption, but it's reasonable in many cases, then you could figure out that if you are at green and you try to reach yellow, you will likely succeed at reaching yellow because you've seen examples that reach yellow from other similar states, namely blue. So this is a kind of counterfactual knowledge. It's saying that if you were at green and you were trying to reach yellow, you would probably succeed. Whereas for some other state that was not reached from similar states, you might not succeed. So the key idea is to use videos to learn which outcomes can result from which states. And this turns out to be a great way to initialize the value functions, because value functions turn out to make very similar kinds of predictions. So here's the idea. This idea was developed by my student Dibbo Ghosh in a paper called Intention Condition Value Functions. And the idea is that we're going to learn what is called an intention condition value function, or ICVF. An ICVF is a function of three arguments that we're going to call S, S plus, and Z. S is your current state. That's what you see right now. S plus is a future outcome. Perhaps the outcome is open the cabinet. And then Z is your intention. Z is what you were trying to achieve. You can think of Z as a representation of task. You don't have actions in the videos, so Z is a kind of latent variable that takes the place of actions. Of course, the kinds of queries that you typically care about is, will I open the cabinet if I actually try to open the cabinet? But by learning all these combinations, you can actually get a much more generalizable representation. So even though usually open the cabinet will not succeed if you're trying to do something else. If you're trying to fetch a plate, you actually will open the cabinet. So that's actually a little bit more generalization you can get out of it. And we can represent these ICVFs with this multilinear representation using features of state, features of outcomes, and matrix representations of intentions. So phi is a feature representation of the present, psi is a feature representation of the future, and T is a matrix representation of your intent, the transformation it will have on your state. This can be trained from data without actions or rewards using video data by using an offline algorithm very similar to implicit Q-learning. It doesn't use actions and it doesn't use rewards. Mechanically, the method looks very similar to Q-learning or SARSA, so you actually perform TD backups over frames of videos. And it's equivalent to an approximation of something called a successor representation, for those of you that are familiar with it. Okay, but technical details aside, why should we expect these ICVFs to be good for downstream robotic learning? Well, the intuition goes something like this. These intention condition value functions, they can be thought of as expected values of indicators of future state. So it's an expected value in expectation under the policy induced by Z of roughly the frequency with which you'll visit the state S plus in the future. Meaning, if I do Z, will I reach S plus? That's really the question of the ICVF is answering. A regular value function for a policy pi and a reward R is an expectation under the policy pi of the total number of times that you'll see high reward states. If you imagine that your rewards are 0 or 1, it's basically counting how many times you'll get the reward 1 states. So a regular value function answers the question, if I do pi, will I reach S plus with high R? And in the extreme case, if you imagine your task has only one high reward state, then this is essentially the same question as what ICVF answers. If you have multiple states with high reward, it turns out that by linearity, ICVF can answer that question also. So that's basically why ICVF serves as a good initialization for value functions. More precisely, it turns out that you can recover the optimal policy from the ICVF in zero shot just by averaging together the representations of states weighted by their rewards, and then querying the value function with the current state and Z for both the second and third argument. This is similar to the proof for the FB representation. You can also do feature extraction. You can use 5S to represent the value function for downstream online reinforcement learning. And in that case, you can also prove that if you use 5S as the representation and just weight it differently for different actions, you can get a Q function. So you can sort of think of the Q function being formed by putting different heads on top of phi for the different actions. And this is actually provably sufficient for all tasks if the dimensionality is high enough and if we have infinite samples. Now, these are, of course, unrealistic assumptions, but it's a nice kind of completeness result that shows that in the limit, the ICVF really does learn all possible tasks and therefore serves as a good initialization for value functions. So we can use this in a three-phase algorithm. In the first phase, we take the video data and we train the ICVF. In the second phase, we take our robot data and we fine-tune from the ICVF to get a robot Q function, just like in PTR. It's a multitask Q function. And then in the third phase, we would fine-tune to our particular downstream task. And this actually works really well. So we ran this in a PTR style recipe on a variety of challenging downstream tasks with distractors. And in these tasks, VPTR, which is our method, succeeded about 50% of the time, which might not seem like much, but it's a lot better than all the alternative methods. What's interesting is that even if we omit the diverse robot data and just use the videos, that's actually already giving us some non-trivial performance, actually better than if we omit the videos for these harder evaluation tasks. We can also use this with language condition policies, so we can train language condition VPTR that can do things like put the knife in the pan. And you can see that over time, the VPTR value functions look much smoother. They're increasing steadily. The x-axis here is time, the y-axis is value function, as compared to PTR, as well as a previous method called VIP. Okay, but for the last portion of the talk, let me talk about a little bit about how we can learn from a variety of different robots rather than just videos. So one of the recent projects that we did, which is called RTX, we took the bridge data set and also combined it with a variety of other data sources from all around the world. And this was a project led by some folks at Google together with my postdoc, Carl Perch, as well as hundreds of other collaborators. The final data set contained 527 skills, 22 different robot types. It involves 34 different labs and resulted in over 1 million robotic episodes. Now, I could tell you all about the statistics, how many trajectories were from each robot, from each embodiment, and so on, but it's perhaps more effective to actually just see this in videos. So this is just a sampling of the videos. This is from a visualizer prepared by my student Diba Ghosh that shows the range of different behaviors in this data set. And you can see the variety of viewpoints, the variety of robots, and of course the huge variety of tasks. One of the experiments that we did is we trained on this RTX data set In this case, we trained a single language condition imitation learning policy, and then we sent that policy to a variety of different labs and asked them to compare it to the best policy that they had in their particular setting. Some of these tasks are shown at the top and the results are shown at the bottom. On average, the multi-robot policy, which just used an RT1 style recipe, outperformed the best policies that each lab had for their particular setting by about 50%. So you can see that this one multitask policy was trained once, it wasn't really tuned, could actually succeed more effectively than policies that were specially designed in the individual settings. We also trained a much larger policy based on a VLM, based on RT2 at Google, and tested it on difficult language following instructions. So these language instructions are actually out of distribution for the training set, and they require the VLM to use its internet scale pre-training in combination with this multi-robot training to succeed. In this case, RT2X, which is RT2 using the RTX dataset, performed significantly better on these generalization evals, basically multiple times better than the original RT2 policy trained on only the Google data. And this included some fairly complex instructions like put the banana on top of the pan, move the banana near pan, things that were really not seen in the robot demonstration data in this particular domain. All right, so just to summarize, I talked about how there's a spectrum where if we want generalist robots, we need to build models that can use bigger data sets, weaker labels, and make fewer assumptions. And we can go from single task systems to multitask systems, systems that use suboptimal data, systems that use multi-robot data, all the way to systems that use video data. And I think this will make our robots more powerful and more general. And I think in the future, we could combine all of these together to build a unified method that can use all the data. So I don't think that this is about having separate individual data sets, but in the long run, it's probably about combining all of them. Thank you very much for listening.